This is working, right? I can't tell. Am I streaming or not? Okay, there we are. Hi, everyone. Hold on, let me go to Discord for a sec. Where's my Discord? It's not coming up. Okay. Right. So I'm supposed to say words now, huh? About the limit comparison test. Oh, this is very blurry. It's better. Let me see if I can't make this a little bit better. Okay. I don't know. So today I want to talk about the limit comparison test for improper integrals. This is sort of a companion piece to what we learned last time. What we learned about last time, just to review a bit, is this thing called the direct comparison test. That's this box down here in the lower right. The limit comparison test, the direct comparison test, which we're going to initialize DCT, basically says that if you have two functions which are both positive, with one bigger and one smaller, and if you know that the integral of the bigger guy converges, then it must be the case that the smaller guy converges. I mean, it is critical that these things are both positive functions. This would be false without that assumption. So you should kind of think of it like g of x is being squeezed on both sides by f of x and 0, right? And if the area underneath f of x from a to infinity is a finite number, so that the improper integral converges, then that must mean that the improper integral from 0 to infinity of g of x also converges. Does that make sense? Did I say that right? I hope so. But another insight that you can make is that if the smaller guy diverges, so you can think of that as being a situation in which the area under the curve, under the graph of g of x, that area explodes in value, say, so that it diverges, then it must be the case that f of x also diverges. The integral from a to infinity of f of x also diverges. Okay? So that's the statement of the direct comparison test. Now we want to talk about something new today, which is the limit comparison test. So the limit comparison test. This is for which we will initialize LCT. This is also a convergence test. That is to say that it will help you in determining whether or not an improper integral converges or not. Why is this happening? Or this thing just sort of goes very, very out of focus. Oh, maybe can I also say, if you've got any questions, let me see. How do I? So I'm sitting in the voice channel of Discord, and I'm hoping that you can just pop in and ask a question while I'm talking, or of course you can type in the chat and get my attention that way. But the point of live streaming this lecture is so that you can have the opportunity to ask questions while I'm talking. Yeah. Anyway, so where was I? Limit comparison test, right? This is another convergence test for improper integrals. By the way, a lot of what we're doing right now is going to get repeated again, but in the context of what are called infinite series. So, you know, if you don't care about improper integrals, that's fine. It's not a huge part of the course, even though we've been spending quite a bit of time on it just because it occurred during this whole coronavirus thing. But we will talk about it again in the context of series, and you'll see a very similar result here. So it might be worthwhile just to see it in the context of something that you understand really well, which are integrals, before we see it in the context of something which feels more foreign. I'm talking about infinite series. Okay, what to say? Limit comparison test. Well, what I want to say is what the result is. So let me just write it down. So the limit comparison test says the following thing. If you have, again, f of x and g of x are positive continuous functions, on the interval from a to infinity, and if the limit as x goes to infinity of the ratio of f of x and g of x is equal to some finite, or is equal to some quantity L, where L is a one of three things, where L is let's say 0, could also be infinity, we're going to allow that, and it could be a finite number as well. Okay, I mean 0 is also a finite number, let me say a finite positive number, to distinguish these three cases from one another. Okay, so if we have this situation where we have these two functions, f of x and g of x, if it is the case that the limit as x approaches infinity of f of x and g of x is equal to L, then we can make the following deductions. Okay, the first deduction is that if L is between 0 and infinity, so this is the case where L is a finite positive number, okay, then it must be the case that the integral from a to infinity, the improper integral from a to infinity of f of x dx, and the integral from a to infinity of g of x dx converge or diverge together. And what this means is that if you know one of them converges, you can legitimately deduce that the other one converges. And if one of them diverges, then you can legitimately deduce that the other one diverges. They hold hands in terms of their status as convergent or divergent improper integrals. Okay? The other two cases now are going to get covered, where L could be either 0 or infinity. So let's start with when L is 0. If L is 0, so let me just think for a second. If L is 0, that means that, yeah, if L is 0, that must mean, let me make sure I get this right. Okay, so let me very carefully think. if L is 0, so if L is 0, it's kind of like the pace at which f of x is going to 0 is very fast, and it's faster than g of x. Okay, so if L is 0, then what we can deduce is and if the integral from 0 to infinity of g of x converges. Oh shoot, I forgot the dx. Oh well. Then the integral from a to infinity of f of x converges. I'll try to explain a little bit more about why, or intuitively why this might be so, particularly in light of what we learned from the direct comparison test. Okay, but this is the true statement that I wanted to state. Let's see, what else is there to say? So the remaining case that we need to cover is when L is infinity, right? So if L is infinity, we need to say something. If L is equal to infinity, now this is the situation where f of x goes to 0, or it's just getting swamped it's going to 0 faster than g of x is. I'm just sort of running through the heuristics in my head, so maybe don't listen to the things that I'm saying if they don't make sense to you, but rather listen to watch what I write. And if the integral from 0 to infinity of g of x diverges, then the integral from a to infinity of g of x, f of x, the whole point, f of x dx diverges. Okay? That's the full statement right there of the limit comparison test. All right. Let's see. Should be keeping an eye on chat in case there's any questions. Yeah. Is that clear? I can see that there's 3 of you watching, so if you do have any questions, just say something, and if you want me to repeat something, I'm more than happy to do that as well. I have no idea what I'm doing, but anyway. This is the limit comparison test, and it's very important. And in terms of which one is more important, the direct comparison test or the limit comparison test, I would say that it's not close. The limit comparison test is far more important and far more potent as a result. It's much more useful. You'll find yourself using it a lot, actually. Let's see what some of the implications of that are. So let's do a problem. Let's do an exercise using the limit comparison test. So what I want to do is test an integral for convergence. I'll just pick something. Limit comparison test, it turns out, is very good at analyzing the convergence or divergence of an integral when the integrand is like an algebraic function. And by algebraic, I mean it could be like polynomial or rational, or it could involve like square roots or cube roots or powers that are more exotic, like x to the pi or whatever. The limit comparison test is excellent at dealing with improper integrals that look like that, even very complicated things. So let's think about, for example, the integral from, let's say, 1 to infinity of, how about, I'm just making this up off the top of my head, x squared plus 1 divided by x to the 5th plus 4x to the 4th plus 10. And what we want to do is test this for convergence. So remember what I mean when I say that. What I mean is I want you to tell me whether or not this improper integral converges or not, but furthermore give me a good coherent argument as to why it converges or not. Yeah? Okay, so let me tell you. The way that we're going to use the limit comparison test typically is the following. We're going to be given an improper integral. There's the improper integral that we're given here, okay? And we're going to let f of x, the thing playing the role of f of x in the statement of the LCT, we're going to let f of x be the integrand, the thing that we're taking the integral of. And g of x, well, that's going to be something that we will choose, that we will have to determine in the hopes that the g of x that we choose will satisfy this condition, that this limit is something we can compute. But also, if we choose g of x really, really well, then we can find ourselves hopefully in this first condition. This first condition is the best one, because we don't have to deal with this goofiness of these if-then statements. This one right here is the nicest to be in. So if we can get L to be a finite number by choosing g of x appropriately here, then we're very happy, and because it must be the case that these improper integrals sort of, again, hold hands with one another. They converge or diverge together. So let me try not to explain how I'm going to come up with the g of x here. This, again, is going to be my f of x. That's going to be my f of x. But a question that you're going to have when what I'm about to write down is, how did Professor Inouye come up with that particular g of x? And I'm not going to say it right now, but I promise that I will when I'm done with this example, okay? So here's what I'm going to do. Let g of x, so this is my solution. Let g of x equal 1 over x cubed. That's what I'm going to do. 1 over x cubed. Now you're probably saying to yourself, why? Or you might be saying to yourself, how in the world did he come up with that? And I will explain that. So somebody asked, is f of x just the denominator, or is it the whole function? No, f of x is the whole function. So let me actually box the whole thing. I see why you're confused. No, f of x is in fact the entire integrand. Now I'm going to let g of x be 1 over x cubed. And what I'm hoping, I'm not actually hoping, I actually know it for sure, but what I'm hoping is that if I look at the limit as x goes to infinity of f of x over g of x, that I'm going to get a finite number L. That's the hope. In fact, I already know what it's going to be. It's going to be 1. But let's just verify that by actually doing the limit. Okay. Then the limit as x goes to infinity of f of x over g of x, what is this? Well, it's kind of a mess, but let's see what it is. It's the limit as x goes to infinity of, so upstairs we're going to have this crazy guy, x squared plus 1 over x to the 5th plus 4x to the 4th plus 10. That's what we have upstairs in the numerator. That's f of x. And then downstairs in the denominator, we're going to have 1 over x cubed. You can think of it like what we have is a fraction of fractions, so maybe we can write something like that to be absolutely clear about what's happening. Okay, well, now we can just do the algebra, or whatever you call it, the arithmetic, to simplify this or to rewrite this. If we do so, what we obtain is the limit as x goes to infinity of, so I'm going to flip this guy upside down, right, and multiply it by the numerator, right, because dividing is the same as multiplying by the reciprocal. So what we get is x squared plus 1, I'll go slow, x to the 5th plus 4x to the 4th plus 10 times x cubed over 1. So x cubed over 1 is the reciprocal of 1 over x cubed, and I'm multiplying it by the numerator. And we just do the multiplication. We get the limit as x goes to infinity of, so I'm going to distribute this x cubed into here. So I get x to the 5th plus x cubed divided by x to the 5th plus 4x to the 4th plus 10. And if you're observant, maybe what you see is now we have a situation where the leading term, that is to say the highest degree term in the polynomial of the numerator and the polynomial of the denominator are in fact exactly the same. Okay? What we do next, so if we want to evaluate this limit, we have two options. We can do L'Hopital's rule 5 times if we want to, and because this is a limit of the form infinity over infinity, we could do L'Hopital's rule 5 times, or we could do the following trick, which is, I think, much more efficient, which is to factor out the highest degree term from the top and the bottom, from the numerator and denominator. If we do that, what we get is the limit as x goes to infinity of, so upstairs we're going to have x to the 5th times 1. So I'm factoring out x to the 5th from the numerator. Okay? So when I factor out x to the 5th from x to the 5th, of course I get 1. But if I do it to x cubed, what I'm left with is 1 over x squared. Hopefully that's clear. Okay? So in going from this numerator to this numerator, what I did is I factored out an x to the 5th. And I'm going to play the same game in the denominator now. 1 plus 4 over x plus 10 over x to the 5th. Hopefully that's clear to everybody. Okay? And now the point of this move is that these terms kill each other. X to the 5th and x to the 5th, upstairs, downstairs, are a common factor, upstairs and downstairs, so we can cancel. It's like the most important fact about fractions. Further, please note, what happens to these terms which all have an x in the denominator, positive power of x in the denominator? What happens to those terms as x runs to infinity? For example, what happens to 1 over x squared? 1 over x squared. So when x is like 10, this is 1 over 100. When x is like 100, this is like 1 over 10,000. When x is 1,000, this is 1 over a million. When x is a million, this is like 1 over a trillion. In other words, the larger that x gets, the smaller and smaller, that is to say closer and closer to 0, 1 over x squared becomes. And so it should be obvious that these things, for example, 1 over x squared goes to 0. So I'm just going to cross it out. And similarly, 4 over x goes to 0, as does 10 over x to the 5th. All these terms die in the limit. Okay? So that this limit, what's left over as x goes to infinity, the thing which is important is this 1 right here. If I use red, will that be confusing? Maybe I'll use blue. Is this 1 right here and this 1 right here. Those are the things that are sort of survive as x goes to infinity. And so this limit here is equal to 1. And this 1 is what's playing the role of our L. Of L in the statement of the limit comparison test. This 1 right here is the same as this L right here. All right? Okay. So now, given that that's the case, we can look at the trichotomy presented by the limit comparison test and determine which of the 3 cases that we are landing in with this choice of f of x and g of x. Well, it's pretty clear that where we're landing is this first case, right? L is 1, so it's between 0 and infinity proper. Okay, and so what that means is LCT implies that the given integral, so by the given integral I mean this integral right here, LCT implies that the given integral and the integral from 1 to infinity of 1 over x cubed dx converge or diverge together. And I'll write that like this, conv div together. Okay? But what do we know? If you're watching this asynchronously, like on YouTube or something like that, you might pause and try to figure out, what is it that we know for sure? What we know is that this integral here converges. Why? Because it is a p integral with p equal to 3, which is greater than 1. And remember the rule for p integrals. We can go way back in time. Let me see. I have all of this on paper somewhere. I swear that I do somewhere. Remember the statement for p integrals. The statement for p integrals is that a p integral, which is defined to be an integral from a to infinity of 1 over x to the p, is convergent if p is greater than 1 and is divergent if p is less than or equal to 1. Okay, let me just see if that showed up on camera. Yeah. So given that we know that, because 3 is greater than 1, this thing is convergent. Therefore, the given integral, this one here, is convergent. Again, I just want to make this point. I boxed the word convergent there, yes? I boxed it. But the thing which I will get credit for is all of this work here. Okay, this is the work that I want to see. This is, just writing down convergent or divergent, again, that's a coin flip, okay? You're right 50% of the time just by rolling a die or flipping a coin, okay? So I'm less interested in your ability to be lucky and much more interested in your ability to reason your way through to an answer which makes sense, just to be clear. Somebody asks, what if L is equal to 0, okay, and the integral diverges? Yeah, then you can make no conclusion. Right? Because this is an if-then, and maybe this is useful. I usually try to give my Calc 1 students a lot of talk about if-then statements just because they're so fundamental to our world. But maybe that's for another day, or maybe you can ask me. But the short answer to your question. The question is, what if we fall into this case and let's say that this integral here diverges, so that the premises of this statement, if blah, 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 then blah, 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 so that the if part doesn't actually hold. Then you can make no conclusion at all about what's going on with the integral of f of x. Let's just take a step back for a second and look at this solution again. How did we use the limit comparison test to prove that this was a convergent integral? What we did is we chose g of x wisely, and I haven't told you how I was able to choose it wisely, though some of you probably were able to divine through the process of the solution how that came to be. But we'll talk about that more. I chose g of x. I let f of x be the integrand of the given integral. Okay. I chose g of x wisely. I computed the limit. I found that the limit was some finite number. I looked at which of the 3 cases of the LCT I fell into, and then I proceeded from there and was sort of crossing my fingers that I would be able to get a nice conclusion out. Okay? That's sort of the idea. All right, so let's talk about how I chose that g of x. How did I know that for this f of x, this particular g of x would work? I mean, there might be other g of x's which work, but what we would like to have is the safety and security of knowing that a particular g of x that we choose will actually work out for us. Okay, so for that, we should say something about polynomials. Let's see, how much time have I been streaming? Holy crow, about 30 minutes already. Okay, let me say it like this. And there will be more sort of color and detail on this statement in the worksheet that I'm going to give you today. But here's the statement that I wish to make. Polynomials. So here's the statement. When x is very large, okay, so a notation, so when x is very large, so I mean like x is like 1 trillion 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 or whatever, just an enormously huge number. We have notation for this actually. What we write is that x is much, much, much greater than 0. This is actually standard notation, okay? When x is very, very large, okay? Here's the fact that I want to state that you should carry with you for the rest of your life because it's incredibly important. When x is very, very large, a polynomial p of x is well approximated by its highest degree term. This is the fact about polynomials that I think is very important for you to know. Okay? So what am I trying to say? For example, I'm trying to say that if you look at something like 3x squared plus 15x squared plus 1, that if, and we call this p of x, if x is very, 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 very large, so it's not just one alligator that would prefer to eat x, it's actually 3 alligators that would prefer to eat x, okay? If x is extremely large, then p of x is approximately going to be equal to 3x squared. In other words, we can ignore, oh shoot, this is insane. Okay, wait a minute, hold on. I wrote this completely badly. I wrote 3x squared plus 15x squared plus 1, but let's make this 3x cubed. Let's do that, 3x cubed. Now the highest degree term in this polynomial is 3x cubed, okay? And what I'm saying, and I'm right, is that p of x is well approximated by 3x cubed. Okay. Let's see. There's a number of ways of showing that. What I could do is like overlay the graph of 3x cubed plus 15x squared plus 1 with the graph of 3x cubed, and then zoom way out so you can see what it looks like when x is very, very large, and you'll see they're similar. But you know, I don't know, like what if we were to stick in, like say something like 1,000 into here. So like p of 1,000, what is it? Well, 1,000 cubed is 1,000 times 1,000 times 1,000. I believe that's 1 billion. 1 billion times 3 is 3 billion. So this contributes 3 billion. This is well, 1,000 squared is 1,000,000, so that's 15 million, and that's 1. So we have 3 billion, 15 million, and 0.0000001. I believe p of 1,000 is that value. Okay? But if we look at 3x cubed, and we evaluate this at 1,000, okay, this is equal to, well, like we said, 3 billion. And although p of 1,000 is 15 million more than 3x cubed, as a proportion, 3x cubed is doing a hell of a good job of approximating p of 1,000, like percentage-wise, right? The error between these two numbers is like less than 1%. And as x gets larger and larger and larger, okay, the discrepancy percentage-wise between p of 1,000 and 3x cubed will only get smaller, okay? Just, that's true. And again, I'll have a table of, I don't want to belabor this point too much now, but I'll have a table of values in the worksheet which really make this manifest, very apparent, rather, okay? Cool. So that's the statement for polynomials, okay? And what we can do is extend such a statement to rational functions if we want to, because rational functions, after all, are polynomials over polynomials, okay? And what we can do to approximate a rational function really well is to take the highest order term of the numerator and divide it by the highest order term of the denominator, okay, by this principle here, and that will give us a good approximation to a rational function, again in the regime where x is a super large number. The basic idea for how you choose g of x, so let's go back to what we were doing previously. The basic idea for how you choose g of x in the limit comparison test is you look at the integrand that you're given in front of you and you ask yourself, what does this integrand look like when x is very, very large? And if you're able to come up with a nice approximation to f of x when x is very large, you use that approximation as your g of x. Okay, I'm going to say it again because I think it's important. The question that I want to ask and answer is the following. Given an integral like this, an improper integral, how do you choose g of x? How did I choose g of x to be 1 over x cubed, for example, in this particular example? What you do is you look at your integrand and you ask yourself, what is a good approximation to that integrand when x is very, very large? If you're able to come up with a good answer to that, that approximation is a good choice for g of x. In looking at this example, for example, in looking at this exercise, for example, what is a good approximation to this f of x? Well, the numerator, okay, given that it's a polynomial and its highest order term is x squared, the numerator here is approximately equal to x squared when x is very, very large, again. And the denominator, given that it is a polynomial, is well approximated by its highest degree term, which is x to the fifth. And so the way that I'm going to choose so the rational function as a whole is going to be well approximated by x squared over x to the fifth. Does this make sense? And x squared over x to the fifth, I know, just by basic algebra and rules of exponents, is 1 over x cubed. So that's how I came up with 1 over x cubed. Hopefully this is making sense. Let me write down what I said. So going back to LCT. Now, the question is how to choose g of x for a given f of x. You're given f of x, how do you choose g of x? Here's one answer, which doesn't always work. I'll just say that because I don't want to get sued by you. Doesn't always work 100% of the time, but it works very, very often. Choose. Look at f of x and look at f of x and approximate it when x is very, very, very large. Choose g of x to be this approximation. That's the idea here. Okay, so let me give you a problem to sort of test your ability to use this idea. And let's see if you can kill it. So suppose that we have something like the integral of x plus 1 divided by, I don't know, how about x cubed plus 10x squared. And we'll take the integral to be from 1 to positive infinity. And you know what else I'm going to do? Just for fun? Let's put a square root on top here. So for those of you that are watching, and what I'd like you to do is test for convergence. So for those of you that are watching on YouTube, you can pause the video right now and give this problem a shot. If you're watching live, well, I'm too much of a dope to know how to insert a pause into the video. So we're just going to go. Okay. We're just going to solve this problem. Now what I can tell you, and what you'll eventually get to this point as well, is I can tell you like 100%. This thing is convergent. 100%. All right, and the reason I know that is because the numerator here is going to be, by this principle over here, the x plus 1 under the square root is going to be well approximated by square root of x. Whereas the denominator here is going to be well approximated by x cubed. Okay? When, again, this is for when x is very, very large. And can I just say, maybe make a comment that it is only x very large that we really, really care about. Because, you know, if we're interested in the question of convergence or divergence for an improper integral, then we don't actually give too much of a, we don't care about what happens when x is small, right? What we really care about is the behavior of the integrand when x is very, very large. Because the only sort of pathology, let's say, which could prevent this thing from being a convergent integral is this infinity here, right? So, you know, you don't care about what's going on with a patient's legs when the issue that's killing them is their heart, right? What you want to focus on is the pathology, where the pathology is. The pathology of this integral, the thing that makes it improper, is this infinity. And so, of course, what we care about then is what this integrand looks like when x is very, very large. Because x being very, very large means that in some sense, x is in the vicinity or the neighborhood of infinity, right? It's closer to the heart than it is to the legs. I don't know if that makes any sense to you at all, but hopefully it does. So it's the what we're going to use, this is going to be our f of x right here. This is our f of x. Remember what we're using here. We're using the limit comparison test. So this is our f of x. We need to choose our g of x. The g of x we're going to choose, of course, is square root of x over x cubed. And a synonym for that, if you're good with your exponents, is 1 over x to the 5/2 power. All right, at least I hope it is. Yeah, that's right. Okay. And what I know, but which I'm going to work out now, is that if I look at the limit as x goes to infinity of f of x over g of x, that's going to be equal to 1. That will be equal to 1. Okay? Well, let's try to work out that limit. Maybe, and I mean, it's going to look exactly like what I did here, but maybe a bit messier, maybe not. I'll work it out, but you might try to work it out on your own if you've not done so yet. Because, you know, algebra is the big thing here, right? Getting the algebra right is incredibly important, as it always is, right? Okay, so, yeah, let's look at, maybe I'll do this on another piece of paper, but let me just say, well, let's just do it on another piece of paper. So what I want to look at is the limit as x goes to infinity of f of x over g of x. Let's remember what these elements are. So f of x is this box here. G of x I'm going to choose to be 1 over x to the 5/2 power. How come I'm feeling a little scared? Did I mess up somewhere? I don't think so. F of x over g of x. So this is going to, f of x we said was square root of x plus 1 over x cubed plus 10x squared. Now we're dividing by g of x, so that's the same thing as multiplying by the reciprocal of g of x. The g of x, remember, was 1 over x to the 5 halves. So the reciprocal of it is x to the 5 halves over 1. And I'm writing the over 1 just to emphasize that I've taken the reciprocal, right? Now we got to do the algebra here. And so what I would like to do is marry these this expression to that expression. And the way that I can do that is to rewrite this guy here as a square root. Or, well, is that the best way to doing it? Let's see. I'm not sure. That seems a little bit too fancy, actually, come to think of it. But this is, so I'll just write this for now. And then this is what I'm going to do to tackle this limit. I'm going to factor out an x cubed from the denominator. The denominator is not so much of an issue. The issue, the yuckier part, is the numerator. But what I'm going to do is factor out an x from x plus 1. So let me do those things. So I'm going to take x plus 1, I'm going to factor out an x. And what I get is x times 1 plus 1 over x. I hope that's clear. And then we have our x to the 5 halves still hanging out. Downstairs, I'm going to factor out an x cubed. I'm factoring out the highest order term when I can. I'm going to have 1 plus 10 over x. Now, the square root of a product of x times 1 plus 1 over x, the square root of a product is the product of the square roots. So this is the same thing as the limit as x goes to infinity of the square root of x times the square root of 1 plus 1 over x times x to the 5 halves divided by x cubed times 1 plus 10 over x. You agree? I see I'm approaching my limit. That's okay. I think we're going to get this done. This is equal to the limit as x goes to infinity. Now, square root of x is a synonym for x to the 1/2 power, yes? X to the 1/2 and x to the 5 halves get married. Oh crap, I really hope that... Oh, okay, they get married, and this becomes, what? X to the 1/2 times x to the 5 halves becomes x to the 6 halves. That's the same thing as x cubed. You got to be on point with your exponents to know that, but I expect that many of you are. Of course, now what we see is the beautiful thing, which is that these cubes cancel each other. And what we have is the limit as x goes to infinity of square root of 1 plus 1 over x divided by 1 plus 10 over x. And maybe you're seeing the next play. The next play now is that these guys here both go to 0 as x explodes in value. So this limit is equal to 1. So this 1 then is our L. So now which of the three cases of the limit comparison test are we in? We're obviously in the first one because L is between 0 and infinity. And so, what we have, so we know by LCT that the integral, let me say it like this, the given integral and the integral from 1 to infinity of this g of x was 1 over x to the 5 halves, converge or diverge together. But what do I know? But we know that the latter Does it converge? So by the latter, I mean this integral. Does this integral converge or does it diverge? That's right. Very good. It converges. It converges because p is a p integral with p equal to 5/2. Which is bigger than 1. So the given integral converges. All right. Okay. Well, we haven't really covered a situation in which this limit here is not, when we're not in this first case. But there are situations where these two clauses of the LCT are useful. And those you can look at in your worksheet, okay? So listen, that concludes the lecture for today. I will have a worksheet for you. Probably, I'm going to work on it right now. And that will go out to you on the internet today. I'll put it on the web page. What I'm going to do right now is kill the stream, and I'm going to set up a Zoom meeting. And in that Zoom meeting, you can ask any questions that you might have about, well, anything. And I guess we'll go from there, okay? Oh, somebody asked, is g of x always going to be a p integral? I'll say it like this. When you ask a question like, is it always going to be something? The answer that I'm always going to give is no. But I just want to qualify that no in the following way. P integrals are going to be an extremely rich source for g of x. And you will very often find yourself using g of x to be a p integral. Very often. And let's be more precise, I guess. G of x isn't itself an integral. G of x is a function. But it will be the integrand of a p integral. So that means it's of the form 1 over x to the p, right? Yeah, you're right that it will very often be. And whenever the integrand of the integral that you're given is algebraic, and by that I mean it involves plus, minus, division, multiplication, and powers. Whenever that's the case, whenever it's just an amalgam of those things, and it doesn't involve like signs or exponentials or things like that, as long as that's the case, then you can always choose g of x to be a p integral, as long as your improper integral is singularity free. But again, remember, the singularity case is something that we're not discussing in this class for this semester, as a nod to that crazy virus. Sorry, I spaced out there. That crazy virus. COVID-19. Well, I guess COVID-19, I'm sorry, is the disease. The virus is called SARS-CoV-2, I think. Anyway, okay, so I'm going to kill the stream now. I love you guys, and I probably won't stream again until, or release anything until either Tuesday morning or Monday afternoon, depending on what the reception of this live stream thing is, because I mean, I'm only seeing 3 people watching right now, and so I'm not sure how worth it is for me to wake up at 8 a.m. Unless you tell me that you really like it or whatever, then maybe that's different. Okay, hopefully I can get this VOD onto YouTube. Yeah. Okay. Like I say, love you, and be safe. Have a great weekend. Stay inside. Don't touch your face like I'm doing right now. Do something fun. Okay, bye.